Welcome back to the deep dive.
Good to be here.
Right. Today, we're tackling something really specific. High stakes, you might say.
Definitely focused.
We're doing a proper deep dive into air temperature measurement. And this one is aimed squarely at, well, at you if you're prepping for those ATPL theory exams.
Yeah, absolutely. Temperature, it seems basic, maybe, but getting it right, understanding the how and why, it's critical.
It really is. It's not just a number. It links into performance, safety, flight planning.
Yeah.
And avoiding some really nasty situations like icing.
Exactly. So our mission today, if you like, is to really explore that whole relationship between speed, how you measure temperature, and these key concepts, SAT, TET, and RT.
Static air temperature, total air temperature, RAM air temperature. Got it.
We need to nail down the definitions, the physics behind them, the calculations, basically give you the tools to understand why the exam questions are asked the way they are.
Okay, so let's start right there. The fundamental why. Why does a pilot, especially an airline pilot, need such a precise grasp of air temperature? You mentioned 4 key reasons.
That's right. 4 pillars, really.
The first one sounds pretty dramatic. Avoidance of icing conditions.
And it is dramatic. Icing isn't like turbulence, just uncomfortable. It's an active threat to the aircraft's ability to fly.
How so? What's actually happening?
Well, when those supercooled water droplets hit the airframe, they freeze instantly. And the effects are immediate and cumulative. First, you get a significant loss of lift.
Because the ice changes the wing shape.
Precisely. It completely distorts the aerofoil, ruins the smooth airflow. At the same time, you get a massive increase in drag. The plane just doesn't want to fly anymore.
That's getting heavier too, right?
Oh, yeah. The increase in mass can be astonishing. We're talking potentially tons, maybe up to 10 tons on a large aircraft in the wrong conditions over time.
Yep.
Imagine adding that weight unexpectedly.
Wow. And that's not all.
No. You also risk the freezing of control surfaces, ailerons, elevators. If they get jammed with ice, you lose maneuverability. And then there's the engine. Loss of engine power due to ice blocking the intake or damaging compressor blades.
So knowing the temperature helps you stay out of those conditions.
Critically. Different aircraft have different temperature bands where icing is most likely. Knowing the accurate SAT lets you climb, descend, or reroute to avoid those danger zones. It's non-negotiable for safety.
Okay, that's a huge one. Reason number 2, you mentioned engine power and aircraft performance.
Yes. This boils down to air density. Engines, jet, or piston need a very precise mix of fuel and air to work efficiently.
The fuel-air ratio.
Exactly. And the air part of that ratio depends entirely on density. Cold air is dense, more oxygen molecules packed into each cubic foot.
So you can burn more fuel with it?
Right. You can add more fuel, maintain the correct ratio, and boom, more power, more thrust.
And the opposite happens when it's hot.
Absolutely. Hot air is less dense, fewer oxygen molecules. To keep that fuel-air ratio correct, the engine's control system has to reduce the fuel flow.
Less fuel means?
Less power produced. It's a direct relationship, and this is incredibly important for calculating takeoff performance.
Especially on hot days or high-altitude airports where the air is already thinner.
Exactly. That ground temperature reading before takeoff isn't just advisory. It's a critical input for determining if you have enough power to safely get airborne, especially if an engine failed. It's that serious.
Okay, density affecting power. Got it. Third reason. Measurement of speed. This seems less obvious. How does temperature affect airspeed?
Well, remember, we don't measure airspeed directly, do we? We measure pressure differences using the pedostatic system.
Right, dynamic pressure versus static pressure.
And that dynamic pressure reading depends on 2 things: your speed through the air and the density of that air.
Ah, density again.
Always density. So if the temperature is different from standard, the density is different. If the air data computer doesn't know the correct temperature, it calculates the density incorrectly.
Which means the airspeed it calculates from the pressure readings will also be wrong.
Correct. It's a chain reaction. Incorrect temperature leads to incorrect density calculation, leads to incorrect true airspeed calculation.
Okay.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best